Okay, so now we're starting, and we left off approximately here on the Laplace transform. Okay, everyone, we're going to start now. Thank you. On Monday night, we left off talking about special functions, and we were down here in the vicinity. Hopefully, I don't screw anything up here. Of here. And we were talking about special functions, and we mentioned that there was a differential equation for several of the special functions that we were trying to describe. In particular, just as a quick review, we were talking about the exponential integral, which has a definition, obviously, as an integral. The gamma function, incomplete gamma functions, which have various types of definitions. They're also integral definitions. The error function and the complementary error function, they're also integral definitions. And then we work our way down to the Bessel functions. These are the things that are going to be the most important to us at the end of the term. We're not going to use the Bessel functions J0 and J1, or at least that's not my plan, although we're still working on the kinds of homework we want to ask you to perform. You'll primarily be dealing with the modified Bessel functions. I know it's really small to read, but you can probably see it on your screen. It's I0, I1, K0, K1, like we mentioned on Monday night. These have some characteristic behaviors. I0 and I1 sort of behave like exponentials, and K0 behaves like a logarithm, and K1 behaves like 1 over a logarithm. Next is the definition of the Bessel function, as you can see below, and then the definition of the modified Bessel function, which is down here. And the most important thing about the modified Bessel function is its differential equation solution. It has a form. Again, I know it's too small to see, but the solution is y is equal to c1 in, which is the order of the Bessel function, and then c2 and kn. And it's going to be fairly straightforward for us because we're only going to be working in I0 and I1, K0, K1, and the C1 and C2 will be the coefficients we determine from the boundary conditions. Now, many of you, probably it's been a while since you've had a differential equations course. That's why we have a warm-up where we go through some differential equation, some ordinary differential equation work. But when we get to partial differential equations, really in this course, the only way we're going to solve it is with the Bessel function approach or Laplace transform approach. Okay. Next is we'll talk about the petrophysical properties, and this is where it starts becoming a petroleum engineering course. We'll talk about the basic porosity types and permeability, and how traditionally we've sort of thought that we could characterize permeability using Puiseuille's law. We could derive some sort of relationship with Puiseuille's law, which is for flow in pipes, and then we could take that relationship and somehow reconnect it to the flow in porous media concept. The first part of this is really just an introduction to rock properties. I know many of you are in Dr. Ayer's class because I've seen you there. Who's a geologist? Anybody educated as a geologist in here? No? So geologists, the way you make them melt, is you give them a column of numbers and ask them to calculate something. But in all seriousness, they are excellent at describing rock, at understanding, seeing things in multiple dimensions that engineers may not. They have a very holistic view of things. They think about how things behave. They have to, it's sort of like an inverse puzzle. They have to put it back together without knowing, where the picture was on the box. But when you start talking about reservoir properties, they have a completely different view. If you've taken a geology class, you'll remember something called a thin section. And a thin section is where they slice a piece of rock very thin. They usually use epoxy first, and then they look at it under the microscope and try to determine sort of a two-dimensional porosity. Obviously, porosity is three-dimensional. And they also can, at times, try to convert this to a permeability. This section is where we'll look at rock properties sort of from a reservoir engineering standpoint, but we'll also have a little bit of geology in there as well. For those of you who may not have been here on Monday, and I think there's only a couple of you, we're just basically going through the syllabus. We discussed that on Monday, and people wanted to do that. So as I mentioned earlier, we do have a concept that we use in petroleum engineering. It's called Darcy's Law. Darcy's Law was first developed or observed in 1857. Darcy was a sanitation engineer. He used an experiment where he was trying to determine how to pack sand in order to filter water. And he noticed that the different packings of sand had different heights of water. So that gave him an idea that there was a relationship between velocity and pressure gradient. In this particular lecture, we'll derive Darcy's law in a so to speak. We'll use Puiseuille's law and then by analogy sort of define it. There was an attempt to derive Darcy's law using Navier-Stokes theory, and that was done in the 50s by a fellow by the name of Hubbard. If you remember, Hubbard was a geophysicist by training. He got really close. There have been other people who have tried to derive Darcy's law by advanced sort of momentum equations and so forth, and they always come back to some sort of a relationship. My God, I look like Donald Trump. I can't believe I just did that. Okay, but they come back to some sort of, here, I'll put my hands behind me. They come back to some sort of relationship where permeability, I just did it again. Permeability and porosity, I'm putting my hands in my pockets now, are related to somehow with a direct proportionality. Again, there were some more advanced derivations after Hubbard, but if you read Hubbard's paper, very clever, very classic, but he ends up in the end saying, well, if permeability has this definition by Navier-Stokes, then it has to have a unique relationship with porosity. There was some work later on, which we'll also talk about in here, where someone tried to derive permeability from fractals. And, you know, if you're going to devote your career to something, then this is probably a pretty good project. His name was Pape. I assume that's, you know, some sort of Eastern European name. And he's got a lot of papers on permeability by fractals. It was funny because in a way it was kind of like the Gaver algorithm. Pape did all this work to derive the concept of permeability by fractals, and then he ended up correlating behavior and just sort of saying, well, I don't know what the exponents are, so I'm just going to make them up. I'm going to say they're 1, 2, and 10, and I'll use a three-term expression because that fit the data that he was looking at. At any rate, you'll see some more of these kinds of derivations in your career. The one thing that Pape's rules showed was that the relationship between porosity and permeability was geometric. It wasn't exponential. Back in 1942 or so, when we were talking about Archie's first work with cores, he was also doing some work with trying to relate permeability and porosity. He published a paper in 1950 relating porosity by a logarithm to permeability. So that's sort of where the rule or the plot, the concept plot of a logarithm of permeability versus porosity came about. Now, some of you are probably mathematicians. Some of you have probably thought about this. Why would there be a relationship of the logarithm of permeability with porosity? Not, you know, the other relationship I was describing is the logarithm of porosity and the logarithm of permeability. It would be a power law relation. But this one is an exponential relationship. We're looking at the logarithm of permeability and just porosity. Why would that happen? Anybody want to venture a guess? Nobody. Well, I just happen to have a list of everybody in here. So who should we call on? This will be like in prison. You pick a name. Now just give me your finger. Okay, right there. That looks good. Mr. Frick, what's your background? Uh-huh. Okay. You want to throw out a lifeline to somebody else? Or are you going to take this one? All right. Have you ever looked at a distribution of porosity and permeability? Is porosity Gaussian? If you take a whole bunch of samples, do they make a nice frequency curve? I'll give you a hint. Okay. And then what about permeability? Okay, we have a helper here. We always get lazy and do it by a logarithm. We scale it by a logarithm, and so we average permeability by logarithmic means, right? So it's sort of logical that maybe that would happen. By the way, there are some people that wrote these really famous books on reservoir engineering that want to kill you if you average by logarithms. Have you seen those lectures? Why? Why are they really angry that we're representing permeability by logarithms? Does Darcy's law represent permeability by a logarithm? No, it's a proportionality. So if you change if you change permeability by a factor of 10, what do you get? A factor of 10 change in velocity or flow rate. But if you take the logarithm of that, what do you get? Something different than that. And that's why these people are really upset that you might think that, although permeabilities may be logarithmically distributed, it is not relevant to relate permeability to the flow of fluids and porous media with a logarithm. So at any rate, that's sort of where I think this came from, that there was a Cartesian or a Gaussian distribution of porosity values and then a log or a skewed distribution. And that's where, I mean, Archie didn't mention that. He just sort of came up with it empirically. But by the same token, and here's an interesting question to pose to the class, pick someone else. Here, I'll hold it this way. You just put your finger. Where's your finger? Right there. Okay. Where's Ruben? Yeah. Sorry. So, what would be another model that we might have if we don't have a relationship of the logarithm of permeability and porosity? What might we have? How about the logarithm of permeability and the logarithm of porosity, which is a power law relationship, right? Okay. Why would we have that? Where would we have that? When would we have that? What could cause that? In order for porosity and permeability to be power law scaled, let's pick on one of the Frenchies. Here, pick a Frenchie. No. Where's Mr. Limon? Okay. In order for it to be geometrically scaled, what would we be saying? We would be saying that the size of the room and the size of the door are scaled the same. Are all the doors in this building the same size? More or less. Are all the rooms in this building the same size? Not at all. So when in nature would we see something where the size of the room and the size of the door are scaled geometrically? Sorry? What kind of scenario would lead to that? You want to throw a lifeline to one of your buddies? He doesn't know. Does he? If you were starting out 120 years ago, almost, and you were going to describe a porous media to your mom, okay, to your mother, how would you do it? Anybody? Go ahead. Sponge. Okay, that's pretty good. I like that. But a sponge is kind of like Swiss cheese. We're not always sure where the holes are. Okay. Yes, sir. Okay, you're getting way too complex. I'm your mom. I don't think. Your mom is Dr. Dattagupta? Okay, but you're answering the question that you want to answer. You're not answering the question I want to answer. I want you to explain how you would represent porosity to your mom 120 years ago. Now you can drop that glass, but that isn't going to explain porosity. Okay, here we go. Here we go. And does it depend on how you pack them? Yes. Okay. So can we derive a relationship based on packing for volume or porosity? And then we can see how the holes align and how the area that fluid could pass through. What do you think? Is that a scaling law? If all the balls are spheres, does it matter? Explain. No, if they were all spheres. The only thing that matters then is how you pack them. They could be small spheres, they could be large spheres. Now, I'm not talking about mixing them yet, which is what Dr. Dattagupta was talking about. I'm not taking really small spheres and putting them inside of the space of the bigger ones. I'm just saying, is there a scaling law there? Yes, there is. Okay. So in order to have a scaling law where we're looking at porosity and permeability being a power law relationship, you would have to have some sort of complete uniformity in the material. Do we have cases where we have complete uniformity in the material? Where are you from in France? Nice? I don't know where that is. Okay. So you go to the beach? Okay. Is all that sand the same size? Aha. What's the permeability of that sand? What's the porosity of that sand? You haven't thought about it, have you? But it's all worked over millions of years or thousands and thousands and, well, let's say millions of years, and it's all been rounded, okay? So if we start looking at beach sand, is that going to be a good analogy for spheres? It's about as good as we're going to get. So if we're looking at unconsolidated, highly sorted materials, we could see a scaling like that. Okay. I'm just trying to build concepts in your head. Okay. We're going to go through this in a lot more detail. Okay, capillary pressure and relative permeability. And everybody who thinks they know something about capillary pressure and relative permeability, I have no idea, but I've had 2 requests in 3 days from people wanting to have access to data or have more knowledge about these fundamental relationships with capillary pressure and permeability. I guess we could ask people to, I better take this. Excuse me. Yes. Okie dokie, thank you. This is America, right? You would never take a phone call during class, right? Would you? Huh? Oh, I can do anything I want. So I could just drop the mic now and leave. Well, that was a phone call for you. Okay. So we're going to derive a capillary pressure relationship for a single tube. Can we then take, I've already told you that conceptually we can't take a single tube and represent and then make it an infinite number of tubes and make a porous media. But can I take a single tube concept and then, not again, this doesn't look like the same number. Do you want to take this call? I better take this call. Yes. Just like I put on the list, 319 Richardson Building on campus, corner of Spence and Ross Street. Richardson. Right now I'm in the middle of teaching a class. You were supposed to be here a while ago, so I don't think I can come down. I could probably send someone. Andrew, why don't you go stand in the street and talk to this lady until she finds where we're at. He's moving kind of slow. All right. So now I'm completely disoriented. The people in distance learning land probably think I've lost my mind, which isn't unlikely. But can we take the concept of a capillary tubes and then bundle them together? Logically, can we do that? Maybe. How long have we been looking at that theory? What year is this? It's about 80 years that Purcell, Berdeen started looking at taking bundles of capillary tubes to represent a capillary system. Is it correct? Is it conceptual? What are its limitations? Who wants to take a shot at that? Pick somebody. Just use your finger. Yeah, there you go. All right. Ching. How's that? I can see that. Ching Hines? That's you? No, that's you. Okay. I forgot the question. Okay. Is it too ideal to take a bundle of tubes? When we do the capillary pressure lecture, conceptually, a single tube, that makes sense. But then we start having a bunch of tubes. How do we represent that? Is it too ideal? Sorry, is it too conceptual? What's your opinion? You want to throw a lifeline? Here, pick a name. Don't look, just use your finger. There you go. Mr. Burkhart, where you at? Okay. What they do is they pick the longest names, okay, just so you know. Okay. So what maybe if we had some sort of a factor that we multiplied it by, but then we would have to multiply every tube by a factor. This is really getting. How many tubes are there? It's an infinite number. This is really painful. But maybe we can do something like conceptualize it and, say sum up the tubes. Not sure how many there are, but we could sum them up. And then if we assume, sort of an infinite distribution, we could have an integral, that sort of thing, which is what that equation is. But what if we looked at a tube? If we look down a tube, would we see this or would we see this? Could tubes end up touching pieces of other tubes and things like that? Yeah. Okay. So conceptually, we can fix this. We can make this work in the way that we want to use the concept of a bundle of tubes. Why do we want a bundle of tubes, class? Anybody? Okay. For what? It's staring you in the face. Mm-mm. Sorry? More. What's our relationship? What's our equation of motion in petroleum engineering? Darcy's law. So we could estimate permeability. Ah, okay. And if we can estimate permeability, then what can we do? We can then estimate relative permeability. Okay. That might work. We'll see. I think my phone and my student are gone. So one of the things that we were able to do is we were able to define a dimensionless capillary pressure function based on some work by Brooks and Corey. It is a power law capillary pressure function. Why do we use power law capillary pressure functions? What's the easiest word? Because we're lazy. Okay. Can you integrate a power law function? Yeah, it's easy. So when we integrate that power law function and then we substitute it into the definition of permeability, guess what we end up with? The so-called Corey relative permeability relationships. So those things you use in simulators, okay, that's where this comes from. It all sort of makes sense now. By the way, what does the Corey parameter represent? You wouldn't know this, but it represents the curvature of the capillary pressure curve. Okay. So it's an indicator. All right. I'm pretty bored now with capillary pressure and so forth. Now we'll talk a little bit about electrical properties. This is not a course and not a topic where I'm an expert, but I thought we should talk a little bit about electrical properties of rocks, primarily because Archie, during World War II, he was in Houston. It was hot. He was tired, and he needed to do something for fun. He worked for Shell Research Center, so he electrocuted some rocks. He put electricity through them, and he tested their resistivity, and he noticed that a relationship of the resistivity at 100% saturation with the resistivity at it was a relationship of the resistivity at 100% water saturation to the water resistivity. That relationship correlated extremely well with porosity. Hello. Yeah, we got to give her a tip, right? You guys give her the candy bucket. Just set it there on the corner. Just set it on the corner. Don't come up here. Here you go. Oh, she wants a signature. That's what it is. Let's see. Which one's mine? All of them. I don't think I gave you enough. Are you sure? You're never going to get anywhere in life unless you tell people what you're really worth. All right, thanks. All right, where's Mr. Lanson? Come to me. What's the worst job you ever had? Washing what? Oh, sorry. I misheard you. Here, you're the garçon. So what Archie noticed is that there was a unique relationship of porosity with this resistivity factor. Now, nobody in here understands baseball, right? Ruben, you a little bit? Yeah? Tell me about baseball. Sorry? That's not what I'm looking for. Let's go to the next one. Yeah, I got the email today that the size of the plate is 17 inches for everybody, whether it's Little League or Pro Ball. So, nobody's going to make the plate bigger for you when you're a kid. The last time I watched a baseball game, my son was about 7 years old, and somebody lost their temper and threw their glove at the runner. So, of course, when I was growing up in Louisiana, we lost our temper. We threw the ball at the runner. So, all right, next, tell me something about baseball. Back row. Nothing. 9 innings. Okay. Anything else? Okay, so if you hit the ball once out of 10 times, how much do you get paid? Not too much. You better have some other skills. Okay. What if you hit the ball twice out of 10 times? Sorry? Okay. What happens if you hit it 3 times out of 10? How much do you get paid? How much? A lot? Okay. Well, what if you hit 4 times out of 10? Thank you. When's the last time somebody hit 4 times out of 10 in a season? I thought the last guy was Ted Williams, but whatever. Okay. And how much money would he have made now? Mr. Lawson? Yeah, exactly. That's right. So 4 times out of 10, you get all the money. So Archie, he hit he hit the ball a lot, but he had a couple where he missed. You want to hand out the pizza too, or no? Okay. You want some help? No, no, you're not. Here, let's find you a helper. There's some, what do you call it? healthy pizza in there, vegetarian. So, do you think that why would the resistivity of the form or why would the resistivity be related to the porosity? Somebody tell me that. What's the easiest way to explain it? The volume of the electrolyte and the resistivity would be proportional, right? That makes sense. Okay, so here's where Archie made a boo-boo. Archie said what? He said that permeability and resistivity are related. If that had been true, we wouldn't be here. We wouldn't need well testing. We wouldn't need production data analysis. We wouldn't need any of these things because you would just run a resistivity log and you'd be able to estimate permeability. But he showed a very convincing plot that permeability and resistivity were related. We're going to talk about that later. There's a good story behind it. I know you want me to tell you the answer now, but then you wouldn't come to class for the next couple of months waiting for it. Okay, as I mentioned, this is a little bit out of order. Here's the approach for estimating relative permeability, and it's based on, this is the Corey approach. We'll derive that in here. And then again, some more on the Corey approach over here. Now we start to get into how things flow in porous media. Everything else up till now was sort of static. And I'll go through this really quick. We have steady state concepts for laminar flow. This is the same thing that you would have for Poussouillet's law and pipes and that sort of thing. So here we'll derive the relationship for steady state flow based on sort of a Poussouillet's analogy. We'll also derive some relationships for gas. Gas is unusual because gas is much more compressible, so we have to take that into account. We'll derive the steady state skin factor, which is, where's Mr. Lawson? Can you step up and walk to the door there? What's that can looking thing in front of you, behind you now? Can you hold that up for everybody? Yeah, just, okay. What is that, class? Nope, that's the skin factor. Okay. We don't really know how to define it. Would you eat out of that trash can? No. One time in well testing class, I was trying to explain the skin factor in terms of, it's got a lot of stuff in it, but we don't really know how it is. It's an additional pressure drop due to something. It's a non-ideality. And the first way that you would derive the skin factor is how? You would assume some sort of a steady state pressure drop, and that's exactly what was done. So at any rate, somebody put a little cake in the trash can, and it was still sort of sealed, So I took it out and I ate it. The whole class was, sick and complaining and everything else, but I was okay. I didn't mind. All right. So we'll talk then about the concept of non-laminar flow. There's a concept by Klinkenberg. He was about the same time as Archie, early 1940s. The Klinkenberg effect is a low pressure effect. Are we in a low pressure environment right now? Yes, we are. Okay. So if you're a molecule of gas and I have you in a flow stream, the higher the pressure, the more you behave like a liquid. The lower the pressure is, what happens to the molecules? They sort of diffuse, and for a liquid, the rules are that there can be no slip at the wall. But for a gas, those molecules can slip against the wall. This is a low pressure effect. This is the Klinkenberg effect. It happens in the laboratory, okay? For pressures less than maybe 200 to 300 psi, what was that, 20 bar, 25 bar, something like that. And you're thinking, well, who cares? Read the Klinkenberg paper. It can be a factor of 10. The permeability that you calculate due to gas slippage, because the pressure drop is less because the molecules are slipping rather than acting like a film. And so it's usually a factor of 3 or 4, but it could be even a factor of 10. Why is this important, class? How many of you have worked for a living? Anybody here? served as a reservoir engineer, served as a, no? Ever ordered a core study? Ever done anything like that? So when you buy a core study, when you give the laboratory a piece of core and you say, I want you to estimate porosity and permeability, what do? Well, they take a device and they cut a piece out of it, okay, and then they shave the ends off. They make it a perfect cylinder, and then they put it in this device where it's usually toluene or some other chemical solvent, and they boil it for overnight or a couple days. They may use methanol to get the salt out of it. And then what? They put it in a device that looks like sort of a carnival Ferris wheel on the ground, and the device takes a gas, could be helium, could be air, could be carbon dioxide. I'm not sure exactly what they use the standard for. I think they're using helium for porosity because helium will go in the smallest spaces, and they're using air for flowing through it. And the machine is automated, and it gives you some readings, and there's your porosity and permeability, right? Except what? It's uncorrected. Uh-oh. And I mentioned that it could be off by a factor of 3 or 4. So that's something you have to consider whenever you're, asking for a core report. By the way, you tell them that you want them Klinkenberg corrected, and they'll set the device to do that. Next is material balance. We don't have any chemical engineers in here, right? He's not here tonight, so we can't torture him. So material balance is simply a mass balance on the system. And what we'll do with material balance is just go over the material balance for a dry gas and the material balance for a liquid. Back in the late 1950s, a fellow by the name of O'Day, who stood about this tall, well, I mean more like that maybe, he was working for Mobil, and he and Javelina created a solution for plotting the material balance as a straight line. O'Day also did a lot of work early on in well testing. I mentioned to you that he also described I mentioned this in the previous class, that when the paper came out on naturally fractured reservoirs, he wrote a rebuttal paper to it and basically said there was no such thing. He probably regretted that in his later days. But this is why you shouldn't write papers unless you know exactly what you're talking about. Then pseudo-steady state, and we talked about steady state being a fixed pressure distribution. We didn't do that, but that's what it is. It's a fixed pressure distribution. Well, pseudo-steady state is sort of a fixed pressure distribution that changes with time. So the pressure distribution, they're parallel as a function of time. And we'll talk about that later on. I could make you do a trick right now, but I won't. Ruben remembers what it was because I made him do it in the summer to explain pseudo-steady state. Now we start talking about deriving the diffusion equation, and you're not going to like this part very much. This is the derivation of the liquid flow diffusivity equation. All the details are given, so this one's easy. And then we come down. I can guarantee you whenever we get course reviews, everybody hates the derivation of the diffusivity equation. And then we derive the diffusivity equation for gas, and that's sort of similar to the liquid case. It's not really all that bad. There's a lot of algebra involved, but it's not horrible. The important thing is that deriving the diffusion equations allows you to see where the nonlinearities are. Now, we haven't talked a lot about that, but we start from fundamental principles and we derive from the mass balance, the continuity equation. That's what its name is. We then apply the equation of motion, which for petroleum engineers is Darcy's law. We apply equation of state, which could be that for a constant compressibility liquid, which is really easy, or it could be for a real gas. Both of those will be done in that derivation. And what we end up with is still an equation with some nonlinearities. What's the problem? How do you solve an equation with nonlinearities? You got two choices. Sorry? Ooh, I like that. Okay, but we can't get all the nonlinearities out, can we? We can linearize the left-hand side with pseudopressure, But then the right-hand side is still nonlinear because it has what? Viscosity and compressibility in the denominator, and they're varying as a function of pressure. And in order to, pressure is the variable we're trying to solve for, so in order to do that, we would have to make some assumptions about that. Now you can then linearize the differential equation using a pseudo-time, which was really popular in the 80s, but it doesn't help you to solve the equation, and you'll see that. So the way to do this is numerically, and I mentioned this on Monday as well, that this equation actually that I have circled here is the first reservoir simulator. They did solve it, as you said, with pseudo pressure, or actually I think at that time they may have they would have used pressure squared. That was Aronofsky and Jenkins. And then a little bit later, Russell, Goodrich et al. Came along, and they derived, they worked for Shell. They derived a methodology for solving this differential equation in terms of a pseudo pressure. Then Ramey came along, and he derived a little bit different pseudo pressure. And it was a really interesting thing, because had Russell, Goodrich et al. Won, had they did publish first, but they didn't win the war. Ramey was a bigger name. They actually published a normalized pseudopressure, which is my preference here. The normalized pseudopressure gives you a variable that looks, smells, and tastes like pressure. The pseudopressure in a normalized variable is PSI or bar or whatever. The pseudopressure in Ramey's equation is non-normalized. And what you're going is, so what, Tom? How many reservoir engineering books, how many gas well testing books would have been better had we only had one set of equations, because the normalized pseudopressure and the liquid equations would be the same form, and we wouldn't have had to have all these other pseudopressures running around. But we did, and that's a historical note. Sometimes you lose, sometimes you win. Now, we work our way down to multi-phase flow. And in the multi-phase flow derivation, and this is where you're really going to hate me, we derive the oil, gas, water relationships, and then we combine them. And this is going to be pretty mind-numbing, I want to warn you. How do you think we're going to combine multi-phase relationships? We're going to have to make some assumptions. Anybody want to tell me what kind of assumptions we'll have to make? Sorry? Yeah, that's not the big problem. We do have gas miscibility in water, and that's not a real problem. Of course, we have gas miscibility in oil. Both of those are accounted for. Okay, and capillary pressure is 0, which we know isn't really true, but we can do that. What's next? What? Sorry? Loud? Gravity's not. I grant gravity and capillary pressure, yeah, but what's the biggie? Sorry? Saturation what? Saturation gradients. We're going to have to assume that saturation gradients are very small. They're negligible, okay? And that's how we do this. This is a so-called Perrine-Martin approach. So we'll make some assumptions. We'll definitely assume capillary pressures are 0, and we'll assume small gradients in saturations, and hence no gradients in rel perms, because they'll cancel out. And then you can combine these relationships into a total mobility and a total compressibility. So all the algebra works. It all, in the end, it all connects, and it makes sense. But the assumptions that you had to make to get there were pretty substantial. Now, before we start making those assumptions, those equations that we derive are the basis for what we use in reservoir simulation. We could equally use, reduce it and write a reservoir simulator for Perrine-Martin relationship, but that wouldn't really make sense because we want to capture those saturation gradients and so forth. So continuing on, that bend is over here, and these are the final forms that we end up with. And sorry, I have to make another box, but this whole thing is the Perrine-Martin equations. And I can assure you that I'll have to buy you pizza that night because, or that couple of nights, because you're really going to pull your hair out. But once you do this one time, you're never going to be afraid of anything again. And by that, what do I mean? Anybody want to tell me what they're afraid of? Have a little class psychology here? No, no. Anybody afraid of clowns? That sort of thing. Don't you remember Austin Powers? Said he was afraid of carny people, and then in Problem Child, the kid hated clowns. No? All right, well, everybody hates something, and I suspect you're going to hate this, but once you do it, you'll never be afraid of algebra again. I'll guarantee you that. And there is a step-by-step derivation you can follow. Unfortunately, that step-by-step derivation left out formation compressibility. And you're thinking, well, we'll just add it at the end. If I ask you to derive this with formation compressibility, you got to carry it all the way through. Got to make sure the algebra always works. All right, next is the derivation or the definition of dimensionless variables. Who wants to volunteer? Where's Mr. Sarma? Yeah? If we were going to have a universal language, what would it be? Maybe rap? No? See, I made him smile. Do you have a universal language? Math. Ooh. Okay, you're getting warm. Was there a proposal for a universal language? What was its name? Esperanto, okay. Yeah, it kind of like made about as much sense as the metric system in the U.S. Does that make you crazy that we don't use the metric system? Yeah. Hey, just because we crashed a satellite on Mars, because we had a mixture of distance units, we're okay. We admit our faults. Why would we use dimensionless variables? We don't have a chemical engineer here. Does anybody else want to take this on? Who's mechanical? Anybody? Anybody else mechanical? Yeah. Okay, so how'd you end up sitting next to each other? Is your chip aligned or something? Yeah, okay. So did you use dimensionless variables in mechanical engineering? Can you give us a few? The Prandtl number, the Froude number, the Moody number, the Reynolds number, anybody else got some dimensionless numbers for me? Sorry? Sherwood? Is this like a joke? I never heard of the the Sherwood number? Are you sure? This sounds like you're making it up. I mean, I believe you, but okay. Anybody else got a number they can think of or a dimensionless variable? Yeah? Reynolds number, okay. Sorry? Rayleigh number? I've heard of it. Anything else? The Schmidt number, yeah. Okay. You made that one up too, didn't you? Okay. So why do we use dimensionless variables? Why do we spend a lecture on defining dimensionless variables? Scaling, yeah. Okay. Okay, but why would we convert the problem to dimensionless form? What would the real reason be? Okay. You need a hug, don't you? I can see that coming. Anybody else? Okay. This little quadrant over here is really overthinking it. I'm just trying to think of me in my Louisiana public school education, that it makes everything look the same. It converts everything into a simplified math problem. Okay. But there's a ton of work that you have to go through to define the damn things, right? How would you go about defining a dimensionless variable? Just us talking tonight, how would you do it? What's dimensionless distance? You have to have a characteristic length. You have to have a reference length. What's the reference length for a horizontal well? That's easy, horizontal well length. What's the reference length for a fractured well? That's easy, fracture half length. What's the reference length for a vertical well? Uh-oh. Wellbore radius, right? Yeah, except that Muscat, in his book, he didn't know what wellbore radius was because he considered the wellbore to be a mathematical line. So what radius did he use? He used the radius of the outer boundary. So if you're going to call yourself a reservoir engineer, then all reservoirs are circular and the well's in the middle, right? Okay, so there. Anybody want to try something different? How do we define the characteristic pressure? Oh, by the way, how are we going to define dimensionless pressure? Somebody take a shot. Who wants to get called on? Where's Mr. Chaudhry? Is he here today? Yep. How would you define dimensionless pressure? What would be the first thing you'd do? Now think about it as a math problem. Oh, are you going to help him? Okay. You're right, but then we would end up with a ratio that would start at, I don't know. How do we keep that ratio starting at 0? We define it in terms of pressure drop instead of pressure. So the very first thing we're going to do is define, you're right, we're going to decide what our reference pressure is, and we're going to subtract our pressure profile from that. And now we have to have the characteristic pressure drop. How do we get the characteristic pressure drop, class? It's not obvious, but it's going to come from Darcy's law. Okay, so the characteristic length, we got that because we just defined it. Characteristic pressure drop, or the characteristic pressure, it'll come from Darcy's law. Now, where do we get the characteristic time? We got lucky. Where do we get the characteristic time? Yes, sir. Okay, but think about it from the differential equation standpoint. We non-dimensionalize the distance, we non-dimensionalize the pressure, and then everything else that's left over is on the right-hand side. So then how do we non-dimensionalize that? We just stare at it and we say, oh, I'll just divide everything by that. And that's how we get the characteristic time. It'll be different for different geometries, perhaps, but it still is the same concept. Everything that's left over after putting the definition of dimensionless variables in for radius and pressure drop, then we'll use what's left over for time. There may be other dimensionless variables, as these gentlemen were talking about over here, right? There could be a dimensionless fracture conductivity, dimensionless fracture half length, anything else that jumps out at you. There could be dimensionless parameters for naturally fractured reservoirs. There could be dimensionless parameters defined as the ratio of mobility in a composite system, the ratio of diffusivity in a composite system. Generally speaking, we're talking about boundaries, we're usually using the characteristic length to create ratios for that. But I'm sure you could think of some other things if you wanted. All right, so there's all the hard work. Once we non-dimensionalize it, then it's just a math problem. And why do we want to, what's the best way to solve a math problem? Sorry? No, the best way to solve a math problem is by inspection. That's why whenever you work a lot of problems, you can look at something and go, that's Bessel's differential equation. Therefore, I know that's the solution. Now, you still have to go back and you have to determine the coefficients, which is going to be some hellacious algebra and a little bit of calculus, but at least it's a direct exercise. Okay, so next, we talk about the definition of the dimensionless diffusivity equation in radial flow coordinates, and we already talked about that up above, but now we're going to solve it. Okay, now very quickly, class, what do we have to solve a differential equation? If it's a first order ordinary differential equation, what do we need? An initial condition. Sorry? Or an initial condition, depending on how it's defined, but we need one. How many conditions do we need, class? Whatever the power of the highest derivative is, that's how many conditions we need, unless it is a partial differential equation, and then we need a, what? The partial part is time, right? That's going to be the booger, so we need an initial condition. So for partial differential equations, we're going to need an initial condition, we're going to need an inner boundary condition, an outer boundary condition most likely. By the way, I didn't really talk about this, but should our problem start at time 0? Yeah, that would be the best idea. And do you think that when you're defining the initial condition that the behavior in the system should be uniform? Let me put it in simple words. What's our initial condition in terms of pressure? Initial pressure. All the pressure at all points in the reservoir is at initial pressure. How many papers are there written where the pressure in the reservoir is not static, is not uniform? Very, very few. Very few. Book problems you might look at, like for a drum or a string or something like that, they'll have, some sort of frequency applied to it. But for the case of what we're looking at, we're generally going to have a uniform initial pressure condition. Okay. And then what would make the best kind of inner boundary condition? Anybody? Sorry? Right, but that is where the inner boundary is, but what kind of condition would be best there? Constant pressure, constant rate? You choose. Which one do you think is going to be easier? Constant rate. Okay. Okay. And then what about the outer boundary? What kind of options can we have for the outer boundary? We could have a no flow outer boundary. That's where I'm blind and I walk into the wall. Okay. We could have an infinite acting outer boundary. What does that mean? That I just keep walking and I don't ever run into anything. And then we could have a constant pressure outer boundary. Is there such a thing? Really? Constant pressure outer boundary would require a molecule by molecule replacement, wouldn't it? Does that happen in the real world? No. But we will probably solve a constant pressure equation sometime. Constant pressure outer boundary. Okay. And then we have all of our radial flow solutions in the Laplace domain. And then we start to convert them into the real domain. Now, my Frenchies, did you solve all these things in your undergraduate degrees? Laplace was French, oui. Yeah. As was Legendre, as was Pascal and Descartes. Yeah. All those guys. Okay. So the way we're going to do this is we will look at the solution that we're trying to solve and we will break it into pieces if at all possible. Now, there is a trick that we can use, and we'll talk a little bit about this later on. It's called the Boltzmann transform. The Boltzmann transform has exactly one applicable condition for us. It's the constant rate inner boundary condition, infinite acting outer boundary condition. That is the only case the Boltzmann transform works for. But the Boltzmann transform does what? It allows us to redefine a z variable in terms of RD squared over 4TD or RD squared over TD, however you want to reconcile it. And by substitution, that variable allows us to solve the differential equation. It converts it to a common form, if you want to call it that. But everything else we do is going to be with the Laplace transform. Okay? Laplace transform is not going to bite you. It's not going to hurt you. I promise. They may bark, but it won't bite, at least not too hard. Okay, so then we have the solution for a bounded circular reservoir. This is the no-flow outer boundary that was mentioned earlier. I've gone on ahead and added some other conditions where I've allowed there to be flow at the outer boundary, but for all intents and purposes, we're going to solve the no-flow outer boundary. Now, you see all this algebra, and you're thinking, no matter how much pizza this guy buys me, I'm never going to understand this. But you will, I promise. These outer boundary conditions, or the no-flow outer boundary condition solution looks really ugly. Let me pick somebody at random, or they can volunteer. Ned, where are you? Yep, okay. You think you can handle that algebra? Yeah, I like it. Is it confidence, or you've already looked at the solution? Okay. Sorry? But there's so much symmetry to it that what we'll do is we'll take the general solution, we'll differentiate it, and then set it up as two equations, two unknowns, and solve for the coefficients. And that's why we get that ugly rational polynomial of solutions. Okay. How do you break something like that? How do you make it less complicated? Anybody? There's some really neat properties of Bessel functions. And remember, the Laplace transform parameter is inversely proportional to time. So as time grows larger, the Laplace transform parameter goes smaller. So what happens is we have some behavior near zero for that parameter, and some really interesting things happen. And that's where we're able to derive some of these simplified forms. Okay. And then last but not least, we will solve these equations in the real domain, and we'll end up with these relationships like this. Okay? And this is a typical logarithmic approximation or exponential integral and so on. I'm going to jump ahead real quick just to sort of give you some guidance. Next, we'll solve the solution for a fractured well, and it's going to be similar to the solution for a radial flow case. If you were stranded on a desert island and you needed to create a solution for a fractured well, but all you had was a solution for a vertical well, how would you create a solution for a fractured well? You're going to hear this term used a lot. It's called a line source. So you could take that line, and at minus xf, you could place that line, and then you could integrate it over 2xf, from minus xf to plus xf. And don't ask me why we have as our reference length xf, which is half the total distance, but that's the way it is. So anytime you hear fracture half length, there's two fractures of equal length. There can be solutions where they're not equal length, but that's going to be pretty mind-numbing. So what we would do is we would take that vertical well solution as a line source solution and simply integrate it across the line from minus xf to plus xf, and that gives us a fractured well solution. Now, for those of you who are sitting here going, well, that's pretty damn simple, there were a lot of people who went insane along the way trying to figure that one out. Okay? Now, that's if we assume what condition with the well or with the fracture. When you look at a vertical well, the flux coming into that well is uniform across everywhere, right? So hence the name uniform flux. So if we apply a uniform flux condition here, we integrate across there. That's the basic mathematical relationship. How many of you have heard of an infinite conductivity vertical fracture? Not a uniform flux vertical fracture, but an infinite conductivity vertical fracture. So there would be some pressure drop in the fracture with a uniform flux fracture, but there is no pressure drop in the fracture for an infinite conductivity fracture. That means that a fluid particle starting there and going to the wellbore, there's no pressure drop. Is that possible? Or is it a relative thing? When we were talking about the beach sand earlier, you said the permeability would be extremely high, in the 20s of Darcy's, at least in the 10s, which would be nearly infinite by comparison to the formation. So relative to that particle of fluid going from the fracture tip to the wellbore doesn't see any pressure drop. But what if instead we didn't have ultra high conductivity? What if we had relatively low conductivity? That's a completely different problem. Now you have to treat the fracture as a reservoir, as a slab, and you're going to have to solve those equations with that. And up until about 1995 or 96, everybody did this with a numerical solution for the fracture. And then a fellow at Schlumberger spent 70 pages in a derivation, and of course they patented it, so it's not available, but it's a direct solution for this problem. There were some other attempts also by Schlumberger for this. Now, what about a solution with a horizontal well with, say, 100 of these fractures or 200 of these fractures? How do we achieve that? We use superposition of the fractures. Okay. We won't cover that here, but we will do that. That's what you're going to do in practice. Last but not least, in terms of the reservoir solutions, is dual porosity reservoirs. And again, I know this is too small to see, but essentially this is what I was talking about before, that there's a fracture system and a matrix system. The fracture system is the conduit of fluid, so all fluid reaching the wellbore has to go through the fracture system. The fracture system is recharged by the matrix system. The mathematics behind that actually came from Barenblatt and Zeltov. It was presented in 1960. I included that paper in your reference deck, which is in the website now. But Warren and Root came along in 1964, 1965, and they sort of put a fix on what Barenblatt and Zeltov had done, and they were able to present this Laplace domain solution. So it really should be called Barenblatt, Zeltov, Warren, Root, etc. Now, in their case, they made a very simplified assumption about how fluid particles come off the matrix face and go into the fracture. And they used a relationship that was just simply a proportionality with pressure. So it's often called the pseudo-steady state interporosity flow equation, but it is not pseudo-steady state. It just describes the relationship between a particle of fluid leaving the matrix face and going into the fracture system. Later on, Nahurieta and Joshwan, two people working at IMP in Mexico, defined a transient interporosity flow solution. So they actually treated the fracture system as a separate reservoir in the sense that its transfer function was not just a simple proportionality. So a lot of words there and so on. Now, we don't get to this one very often. Usually I throw in the towel. You're tired, I'm tired, we've had a long semester. But what I've done is shown how to derive a solution to the nonlinear gas diffusivity equation using the Laplace transform. What's rule number 0 in this class? Cheat. So how did I cheat? How did I do it? Sorry? No, you're along the right line, but in order to reconcile the nonlinearity, you have to know what it looks like. So if you assume a constant rate and you assume that it's gas, so then you have a P over Z material balance relationship. You can take that relationship and you can reverse calculate all the nonlinearity functions you want at the average pressure level. And then you simply use the Laplace transform and take that in the Laplace domain. You know, nobody's using this, guys, but it is a very clever little solution. I mean, there have been a lot of people that ran up against it and said it was very interesting and that sort of thing. It is a direct solution to the nonlinear gas flow problem, but, you know, it's yet another on the heap of my career of useless things. But it was a very interesting mathematical problem, and it was solved by recognizing that you could represent the nonlinearity because there was a constant pressure or constant rate. Now, the Frenchies, you know, let me see real quick. What school? Okay. No, not name, school. So Canadian, eh? Okay. No Echo Superior, no Polytechniques? No. So I had a student from Kazakhstan who went to Polytechnique, and he, you know, on a scale of 1 to 10, he was about a 12 times smarter than me. But he came to me and he said, I want a really hard thesis problem. And I said, okay, solve this in constant pressure instead of constant rate. He came back to me and he goes, this is a silly problem. I think, you know, I'm not going to waste my time on this. I said, give it some more. He comes back and he says, this is not a silly problem, but it's still a waste of time. And he comes back again and he said, this is an impossible problem. Why did you give it to me? And that's exactly why I gave it to him. It's because how are you going to solve this thing as a constant pressure problem where you're going to have to be updating it? So as a nonlinear solution, no nonlinear solution is going to like a constant pressure condition. At any rate, he did a nice job. Good boy. Sends me a card on my birthday every year. It mostly asks me, when am I going to die? You know, that kind of thing. And yes, of course, he's a manager with Total now, but as everybody wants to be apparently. So the next thing is convolution. And We'll talk a little bit about that when we get to the end of the semester. And it's essentially, we'll derive the convolution in variable pressure and the convolution in variable rate. I don't think you're going to love me afterwards, but it is an exercise that you need to do once in your career. It's not hard, but once you do this, you'll recognize that anytime you use a simulator, this is what's going on in the background. Any kind of reservoir engineering software, this is what's going on in the background whenever they're calculating rates from pressures or pressures from rates. And then last but not least is the wellbore storage. This will be in December. Santa Claus will be coming. You'll be happy. And this is arguably one of the trickiest, worst problems in petroleum engineering. And remember, for those of you who aren't familiar with this, the wellbore is 2 or 3 kilometers long, maybe not quite a third of a meter, maybe a quarter of a meter wide, and it's filled with compressible fluid, and it's tied to this gigantic reservoir. But this wellbore acts as a dampening, okay? How do we overcome that? It is everywhere. It's a tax. We cannot get away from it. So from a reservoir engineering standpoint, when you're performing pressure transient tests, when you shut the well in at the surface, what's happening at the bottom of the hole? It's still flowing. And when you open the well at the top, what's happening at the bottom of the hole? Nothing. Okay? This is the simplest way I can explain this. All the material balance relationships to describe the wellbore relation, all the connection, of course, as usual, we use the Laplace transform to connect the two. Very powerful, and so on. This problem was solved back in the 40s by Van Everding and Hurst. Then it became really popular in the 60s and 70s. And I know you're going, why do you care? Because inside of this, if there were a breakthrough where we could reconcile this wellbore condition, then we could analyze pressure much better during a buildup and a drawdown during shut-in and flow test. It's probably not all that important in the whole scheme of things, but it costs time, okay? And we talked a little bit about this on Monday. If your boss says that you can shut in the well for a day and wellbore storage effects are going to last a month, then why shut in the well? It's irrelevant. And offshore and, in an exploration environment, how long are they going to let you shut in the well? What's rule number 0 in life, kids? Never own anything that eats while you sleep, okay? And whenever you shut in that well and that rig is sitting there doing nothing, do they give you a better rate? No. What's a deep water drilling rig run for these days? $250,000 a day? Yeah, something like that. I was told last weekend, and I'm probably going to get into trouble for this, but that there's a field that was discovered in Gulf of Mexico that, it's proven reserves 4 billion barrels, but nobody's got the guts to develop it because it's in true deep water, and the well costs are too high, the oil price is too low, and it's just sitting there. They had a consortia of companies try to figure out a way to do it economically. 4 billion barrels, light oil. Just that's the way it is. All right, last slide. Math for reservoir engineers. First thing we're going to do is cheat. We're going to approximate, truncate, expand, accept material balance. If you ever cheat the material balance equation, she will come back when you're asleep and beat you to death, I can assure you. I patted myself on the back one time thinking that we had figured out an infill development solution where we cheated the material balance equation. It's kind of like your bicycle tire. When it leaks, you just pump it up some more. It was a great idea, unfortunately, and it matched the data. So in concept, it was a great idea, but it was really stupid looking back at it. But that's what you're doing. You're trying to solve a problem, but the best way to solve it was to account for the leakage, not to try to trick the problem into thinking it didn't leak. Take the derivative of it, take the integral of it, take the Laplace transform. If you still don't have a solution, go back to number 1 and cheat again. Favorite numbers, 0, 1, and infinity. What else do we need? And you'll understand later on. Why did I give 0, 1, and infinity, class? Sure. Give me an example. What would you like your initial condition to be? 0. What would you like your inner boundary condition to be? 1. What would you like your infinite acting reservoir condition to be? Infinity. Okay, so there you go. You want to get away from any kind of numbers that are going to give you a hard time. Okay, so I'm going to stop this lecture because it's the second part of the introduction, and then I'm going to start the other one. So have another piece of pizza. There should be plenty left. Everybody should get 2 pieces. Mr. Lawson, did everybody get 2? Yeah. No? You're not a very good waiter. You told me that you really like this, being a waiter.